Okay, I guess we'll go ahead and get started today. And we're really privileged to get to have Dr. Blum come down. He's taken some time out of his day to come down. He's currently the chair at OSU of the chemistry department, and he's had quite a career in chemistry itself. His area of research is molecular level of plastics and polymers. And he came to OSU from Missouri-Rolla, and he's currently the chair at OSU. He has a host of awards, one of them being an ACS Fellow. He's an active ACS member, and he has been a prolific publicist in that he has over 220 publications currently, I believe. And one of his main instruments that he uses is solid-state NMR to study the molecular level effects of polymers and plastics. And I guess I'll turn it over to you at this point.
Okay, thank you very much, Jason. It's a pleasure for me to be here today. I'd like to tell you a little bit about the chemistry department at Oklahoma State, and then also tell you a little bit about our own research. Maybe some NMR that you'd never expected that you'd see or could do with NMR. As I said before, I came here just 3 years ago, so I've been in Oklahoma just a little over 3 years, and we really enjoyed our time here in Stillwater. I have to say that I did almost feel like I was literally blown in today. It was pretty windy here. I think this has got to be even a windy day for here, or is this just sort of typical?
Like what, halves like this, yeah.
Okay, yeah, with all the trucks and everything stirring up, it just seemed like it was pretty dusty, but the crops are doing well. The natural gas price is up, so it should be prosperity. Oklahoma really has a very low unemployment rate. The governor was just mentioning that it was on the order of a little over 5%, which nationally now is pretty good. By the way, can you guys hear me all right in the back? Okay, I can shout if I need to. So what I'd like to do today is to tell you a little bit about the department at OSU, and I have some information and some brochures that I can share with you. If you're interested in potentially graduate school at Oklahoma State, please let me know. We can arrange a visit and so forth. I'll tell you a little bit about Oklahoma State. It's a fairly moderate-sized university. It's not as big as some. It's not as small as others. But we have about 35,000 students overall. Stillwater campus has about 23,000. About 4,000 graduate students are on campus. So it's a vibrant intellectual community. We just moved into the Henry Beltman Research Center, and our president was very happy that he had just managed to confirm that we had surpassed our capital campaign that raised approximately $1 billion. Now it helps when you have a graduate of the geology department named Boone Pickens, who actually donated on the order of $330 million to the university over the last few years. But some of that has gone into chemistry graduate student stipends and summer support through matching funds. So he's been very generous both to the athletic program and also to the academic program as well. And those funds do not bear his name. So he's a good supporter. And OSU Tulsa has an engineering center on it as well. Oops. Okay. So obviously you know where Oklahoma State is, in Stillwater, Oklahoma. It's a town of about 50,000 people, which for some of you may be on the bigger side. For me, it's just about the right size. It only takes about 10 minutes to get from one side of the city to the other. When we moved to Stillwater, I say here, I guess I'm a greater Oklahoman now. When we moved to Stillwater, we knew we wanted to be someplace that was in the West. And not everybody's comfortable in the West, but I love the West. Oklahoma has a lot to offer, and it just has some things that I really like. For example, if you want to be really important in our neck of the woods, what you really want to do is you want to catch a really big bass. And I think that those values, if you want to be famous, the size fish you catch, maybe the size buck you shoot. I don't hunt, but I fish a little bit. But those values are probably better than some of the values that I've seen on the East Coast and the West Coast, because I've lived on both, and I prefer this kind of environment. So, you know, you're lucky. And I know you grew up here, and boy, it'd be nice to live in Chicago. I grew up in Chicago, and it's nice to live in Stillwater. And for some of you, it might be nice, you know, you grew up around here, and, you know, it might be nice to go to a big city for a while. So I understand that. But Stillwater is a nice place to go to school, and it's a nice place to work for me. This is a couple of students out there. We play cricket on the lawn. This is apparently, so they say, the country's largest student union. You'll often see pictures of the library, and our mascot is this man whose name was Frank Eaton, who you might know as Pistol Pete. And he was a journalist who lived for part of his time. He was an Oklahoma Ranger, and he lived for part of his time in just south of Stillwater, called Perkins. He's famous for shooting his revolver off in the student union, or infamous for shooting his revolver off there. The chemistry department is in this physical sciences 1, physical sciences 2, which is next to it. But we also have 9 of our faculty members in the Henry Beltman Research Center. Henry Beltman was a former governor and senator from Oklahoma. And I believe, I hope I get this right if there's anybody from around there. I think he was from Billings, maybe? You know where Billings is, right? Or you heard of it? Okay. Not too far from Ponca City, just due east of here. So in this building, we have brand new laboratories. You're fortunate to have some nice labs with good hoods there. In our lab, we put a 400 megahertz wide bore NMR in there. What's amazing is this is the 5 Gauss fringe field. In the old days, we couldn't put this machine next to a wall like this with a corridor because the fringe field of these magnets would be way out 10, 15 feet, and now they're only like 3 feet. And that's how close you have to be before you have to start worrying about your pacemaker getting reset or your credit cards getting zapped. But now it's really excellent technology that allows them to be closer. We have an X-ray facility with a protein X-ray machine, small molecule X-ray machine. We have NMRs all over the place. We have 2 private NMR, 2 research group oriented NMRs. Plus we have a 600, a 300 solids, 400 liquids, and we've got just new money for another 400 to replace another solution 300. Still, the organic chemists fight about getting access to the NMR. Everywhere I've been, they're used almost 24 hours a day, and people are fighting to get on their NMRs because they just made this compound and they want to get a quick spectrum, and we understand it. We try to provide the access for them. What I did want to say is, this is more a generalized slide that we have, but we have some excellent facilities with lots of instrumentation, and we have some integrated graduate and undergraduate research. There's a number of undergraduates working in some of the research labs. Right now, we have 21 tenured and tenure-track faculty members. We hope to get up to 24. Our dean knows that we're understaffed, so we're trying to do that. We have 5 chemical professionals, including 2 that are focused on just maintaining our NMRs, 1 on general instruments, and the other 2 on organizing general chemistry labs. So students, when they come in as TAs, are usually TAs for a couple sections of general chemistry, and they will have 30 sections each. And we'll run about 1,500 students through the general chemistry program every year, about 500 through organic with a trailer section of about another 100. So there's a few, and right now, we have 70 graduate students. We actually have more graduate students than undergraduate students. We only have 40 to 45 undergraduates in the program. Part of this is because we're an ag school. We're a land grant school. There's a land grant school in every state of the union. And the land grant schools are like the A&Ms. In fact, we used to be Oklahoma A&M, and that's still part of our name. So A&M is agriculture and mechanical. And so they changed their name to Oklahoma State University at one point. But the biggest college, the biggest program on campus, well, arts and science is actually the biggest, but the one that's sort of written into our charter like no other is agriculture. In fact, a majority of the members of the Board of Regents need to have a background in agriculture. So that is in some respects, the top dog. And then engineering and science come after that. Ag schools are a little different. There are just a lot of people who have lots of practical experience, and it changes the university a bit. But in any case, at land-grant institutions, you will often find biochemistry departments as part of another college. So in our case, chemistry is in the College of Arts and Sciences, but biochemistry is in the College of Agriculture. So we're working together, and so we have a little over 20 faculty members, and they have about 15 or 16. So together we have about 37 faculty members. And we have lots of joint research programs with biochemistry, with veterinary medicine, with mechanical engineering, with chemical engineering, and who did I leave out? Geology. So there's lots of, and physics, there's lots of active collaborations. Oh, microbiology too. And so we're very happy about that. And we're trying to grow the number of undergraduates that we have. I think we could do better. I just wanted to point out that we do have a significant concentration of faculty members in different areas. One that we have more students in than anything else is materials related. The other that we're trying to build a little more is in the bio area. But in the last couple of years since I've been there, we've added the faculty members in red. So Chris Fennell does, I'll just highlight them for a second. Chris Fennell does work in theory. He does simulations. He's trying to figure out how water sits around proteins. Gopan Krishnan is bioanalytical, and he's trying to be able to test for metabolites in blood and other fluids so that you can detect cancer. Toby Nelson does organic and polymer chemistry. He's trying to make polymers that will absorb light and give you electricity out of it. Okay. There we go. Ronald Rahine is organic chemistry, does scaffolds for medicinal chemistry. Medicinal chemistry is one of the areas where we have a lot of work being done. Jimmy Weaver does organic chemistry. He focuses on catalysis. Yolanda Vasquez is in biomaterials. She's trained as an inorganic chemist, but learned that if you take and make these little micro pillars of polymers and stretch out stem cells on them, that the stem cells differentiate into different kinds of cells depending on what the physical properties of the polymer pillars are. So it's this kind of interface between biology and material science that Yolanda is working in. And we expect to have 2 more searches going on in the fall. Sorry this didn't come out very well, but you can check us out on the web or chemistry.okstate.edu. And let me stop there, although I'd be happy to talk about some of the individual faculty research programs. But for the moment, I think I'd like to tell you a little bit about research. And there was a time when, and Jason undoubtedly remembers this, there was a time when chemistry departments made these really fancy brochures and things. But now what it is a fancy web page. But we have some small brochures that have the faculty research interest on it. So if you'd like any information, please go ahead and take some of these. We've got some little guys too that are sort of wallet size. So please go ahead and help yourself to these, and I'd be happy to talk to you about that. But for now, what I'd like to do is talk to you a little bit about some of the research that my group is doing. And in particular, we're going to focus on dynamics of polymers and interfaces. So the focus here is on how small amounts of polymer that are at interfaces, polymers, plastics, fibers, adhesives, elastomers, and coatings. Those are the main places where you find polymers. And there's probably, without joking, 20 billion pounds of polymers that are produced in this country every year. It's more than you could possibly imagine. It's more than I could possibly imagine. But it's the major output of material, it's the major output of chemicals in the United States. So we're interested in what happens when you put these at interfaces. Now, why do we care about that? One reason is, let's suppose you're making something with an advanced composite. Anybody play tennis? What are the best? What are the best? That's a loaded question. What are probably the best tennis rackets made out of now?
Graphite, I guess.
Yeah, carbon fiber based epoxy. So you got a fiber that's a thin, strong fiber like carbon fiber, graphite based fiber, and then you got it in an epoxy matrix. That's the polymer. So polymer based composites are everywhere. Fiberglass, boat hulls, car bodies, golf clubs, pretty much any material that is a composite material like this stuff has filler in it. And so if you want to understand what the properties of those composites are, what you need to do is to know what the properties of the polymer are and know what the property of the filler are, like a carbon black in a tire. But when you put those two together and you predict the properties, like how hard are they to stretch, how hard are they to break, how much can you stretch them when you get to breaking, how hard are they to flex, all the things that you'd really like to know, you do not do a very good job of predicting what the properties of the two together are. Why? Because they're not additive. And the reason they're usually not additive is that if you imagine a hard, brittle fiber, like a glass fiber, a fiberglass reinforced composite, you know, did you ever break open a piece of fiberglass? You know, you see all these glass fibers in there. So, turns out that the soft, pliable polymer at the interface where it attaches to the glass fiber changes its properties because it usually is stuck to the glass fiber. So how do you predict that? You know, all you got is a piece of this stuff and you can just bend it on a macroscopic level. So to try and understand what's going on, we're trying to study these polymers at the interface where they change. And there are some fundamental questions that are really important. What is this glass transition temperature like for an adsorbed polymer? The glass transition temperature is where a polymer goes from a hard brittle plastic to a more flexible rubbery-like material. So maybe you've seen demonstrations where you've taken a rubber ball or something like that and froze it in liquid nitrogen and dropped it. It just goes clunk. It doesn't bounce anymore. You take a balloon, you can freeze it. You take a soda bottle, polyethylene terephthalate, polyester, and you heat it up on a watch glass on a heating mantle. You can see the material go from a plastic to a melt. You can stick a glass rod in there and you can pull out fibers. You can make perfectly fine rugs from recycled soda bottles. So the temperature at which it goes from hard brittle plastic to a soft, rubbery, stretchy material is the glass transition temperature. And so how does that vary when you adsorb it onto a surface? So that's the kind of thing that we're going to study. And I'll show you some examples of how we do that. But I also want to mention that one of the other things where this is important, or one of the other areas this is important, is electronic materials. You know, when you make electronic materials, you want to make chips. And the way to make a chip, a silicon chip, is you usually use silicon. And then what you might do is put a polymer layer down on the chip. And then you might etch away the polymer, and then you might adsorb from vapor some metal to make the connection. But you got this metal and you got this polymer layer, and sometimes you make them get blown away or burned off. Sometimes you leave them there. But everybody wants more and more memory in a smaller box. Smaller package is the right way to call it. And they want to have this material as lightweight as possible and as small as possible, because you want all this stuff in your cell phone, right? So how do you do that? You make the layers thinner and thinner and smaller and smaller. And eventually, the properties of a material like plexiglass are not the properties that a sheet of plexiglass have anymore. They're affected because they're at this interface. And you don't see it if you got a thick layer. But as those layers get smaller and smaller, the interfaces become very important as you go to nanostructured materials. And that's the kind of thing that we're after. So, okay. Did I go to? Okay. So just some of the things from my group that are related to this is we're studying hydrogen bonding with FTIR. Those are studies that one could do here. We're studying dynamics via NMR. We're trying to study the thermal analyses and heat capacities. What are the physical properties of these? By the way, if your surface polymer behaves differently than the bulk polymer, and you've got a chip in there, when the chip gets hot, if the polymer gets rubbery at a temperature that's lower than the bulk material, it expands, breaks this teeny tiny little wire, and you have a failure of your integrated circuit. So it's really kind of important. Also, we're working fairly recently on super hydrophobic coatings. Coatings that you can make with cheap materials that actually can be sprayed on or painted on, and ice doesn't stick. And you can see how you might want to use something like this on an oil well in the wintertime when you get these freezing rains, which I presume you're prone to have out here. We get them in Stillwater occasionally. So anyway, those are some of the things we're working on. And so the polymers that we're going to work on, this is a polymer that is similar to one that you will find in sticky tape. The sticky part is sticky tape. The other side is usually cellulose acetate, or it could be even polyethylene terephthalate polyester. But the sticky part actually has polymers in there that look like this. So it's a polymer. It's a long chain like this that repeats with this is the repeating unit. And it has a carbonyl group in it, which is important to us. And it has a glass transition of about 10 degrees. That means at room temperature, you're above the glass transition temperature, that polymer is rubbery. Now, Scotch tape actually has about 6 components in there. But it's kind of like this. It's kind of like this polymer anyway. It's kind of like, did you ever get a credit card in the mail or a card in the mail and you pull it off and there's that gooey stuff, that rubbery type stuff? It's a lot like that. That's a rubbery polymer. Okay? So when you're above the glass transition temperature, that's kind of what it's like. So a related polymer is polymethyl methacrylate. This is plexiglass. Here's a plexiglass enclosure on a road. But notice the structure is almost the same. It's still a polymer, but it's just got this methyl group instead of the hydrogen group. Just that methyl group alone is enough, because of steric hindrance, to cause the polymer chains to not be able to wiggle as much, because the methyl group gets in the way. And now the glass transition temperature on this material is 108 degrees. It's almost 100 degrees higher because of this methyl group. And the glass transition on a molecular scale is where basically the polymer chains are kind of locked in. They can wiggle a little bit, but after the glass transition temperature, you get these big main chain motions. The polymers are like, I don't know, a bucket full of snakes, live snakes. Below the glass transition temperature, it's like a bucket of frozen snakes. Okay? So, just this difference alone makes a difference in the glass transition temperature. So, the other point is there's a relationship between the physical properties of polymers and things that you can measure. And so, oops. Come on. Uh-oh. I'm puzzled. Okay. We'll do this. Sorry about this. Okay. So a couple of things that we're going to study here are, we're going to look at what happens when you absorb some of these things. And we're going to actually use a polymer that has a deuterium on there. We specifically labeled it. It's not that hard of a reaction. You take methacryl or acryl oil chloride and you hit it with deuterated heavy methanol, and you make the deuterated polymethyl acrylate with D3. And we're going to look at deuterium NMR. And so deuterium NMR, when you study NMR, you probably primarily study hydrogen NMR and carbon NMR. Both hydrogen and carbon have spins of 1/2. And you remember the diagram, you have an energy level when you bring up the magnetic field, you get two energy levels, the plus 1/2 state and the minus 1/2 state. And in NMR, you're detecting the transitions between them. And of course, there's this little tiny effect called the chemical shift, which is everything if you're trying to do analysis of compounds and figure out what they are. But it's only a small perturbation. That's why it's measured in, what do you measure chemical shifts in? Parts per million. It's really a small effect. It is really a part per million in the whole spectrum. So deuterium resonates at another completely different frequency, but it also has a spin of what's known as 1, and so it has 3 energy levels in the spectrum. And the transitions that we'll detect are transitions between 2 of these adjacent ones. But it turns out that this quadrupole effect, quadrupole splitting, and I know some of you might be interested in the quadrupole effect in lithium with some of the work that's being done here. But because of this, there's a dependence on the difference between these 2 frequencies. In other words, these 2 frequencies are not exactly the same for materials that are either solid or semi-solid. And so what happens is there's a spatial dependence, where theta here is the angle between the applied magnetic field and the CD vector. And it turns out that this is kind of like having an X-ray machine. In other words, if you had a single crystal of a deuterated molecule and you put it in the NMR machine, you would see a kind of splitting if the CD was oriented at 0 degrees. And then if you turned it 90 degrees, you'd see a different splitting. That's kind of how people do X-ray structures. Now, in the case where we have polymers that don't have crystalline structures, so we don't have single crystals, we've got polymers that are oriented every possible direction. What we get is the superposition of a whole bunch of these, or a powder pattern. And this looks like kind of the top of Batman's hat. So that's kind of what we see, and we try to interpret what happens to these spectra. Now, deuterium is not very abundant. So if I label with deuterium, and by the way, to make deuterium, it's not that hard. You'll see some old cool World War II movies on destroying the deuterium plant in Denmark. No, in Norway. Because they knew deuterium had something weird to do with stuff, because deuterium's got an extra neutron in it. It's just a proton and a neutron. So they knew that high energy radiation passes differently through deuterium than it does through regular water. But you just boil off regular water and you take the stuff with the highest boiling point, and that has to be enriched in deuterium. And if you do this like 1,000,000 times, you can get heavy water. So, but the point is that there's not enough deuterium around that if you label something primarily with deuterium, you don't see anything else. So all the rest of the sites that could be deuterated that aren't, you don't even see it. All I'm interested in is where I put my label. It has a quadrupole moment, and it's at a different frequency, but it's pretty easy to synthesize with this, and we're going to do some wide-line NMR with our deuterium. Here's an example of what happens with deuterium spectra, though. And the top 2 are just solid spectra. And the top one here is D2O with ice. And the second one here is methyl acrylate that's frozen. And there's different widths in these. And the different widths come about because the mechanism that controls this depends upon the quadrupole coupling constant, which is the product of 2 things. I'm getting a little too specific here, but it's the product of the quadrupole moment of the deuterium nucleus times the electric field gradient. That's how does the electron density vary as you go through the nucleus of the deuterium. Well, guess what? If you have a carbon attached to a deuteron, and you have an oxygen attached to the deuteron, you know that oxygen sucks electrons better than carbon does, right? So the gradient in electron density, the variation of electron density as you go across the deuterium from the deuterium to the carbon is greater for the oxygen compound. So heavy water has bigger splitting than CDs. If you have, here's an interesting case, if I label the methyl group, at room temperature, what do you think methyl groups do? At room temperature, methyl groups do something. What do methyl groups do? In terms of moving, what do you think they do? You think they're static? No, what do? They rotate. Methyl groups whiz around like crazy. You have to freeze them down to about 180 degrees before you can freeze out methyl groups just whizzing around. And because of this, that averages the quadrupole moment, the quadrupole coupling, and so you get a reduced line width that has to do with just the methyl groups going around. That's what I'm trying to show here. And actually, if you had, you've all seen soft soap, right? Soft soap is surfactant with water. If you put heavy water in soft soap, that water moves around a lot, but it forms layers of surfactant, and the water in the layers of surfactant still has a little bit of splitting. And if you just have D2O, it has one single narrow line. So the point here is that deuterium spectra depend on the chemical elements that are involved, but they also depend on molecular motion. And that's what we're going to be focusing on. Here's we do this at 400 megahertz. This is a 400 megahertz wide bore, which no longer exists. That's another story for another day. But it has an 8 millimeter sample size, so we do like 8 millimeter tubes. And we do this thing called the Quadrupole Echo, which, just to make a long story short, has some special features in it. Normally when you do NMR, you can just do a single pulse and collect data. But when you're looking at really wide lines, you have to do something special, because what you're trying to do, and this is a very good analogy, you're trying, so imagine, if you will, that you have somebody who takes a trumpet and they blow that trumpet in your ear. And the next thing you're trying to do is hear a whisper. Pretty tough to do. What you need between the trumpet, as long as the trumpet's not too loud, what you need between the trumpet and the whisper is some time to recover, right? And this happens in NMR as well. You're using the same coil to apply this intense pulse, so you excite all the nuclei of the same type, and then you try to look for this little teeny tiny radio frequency signal. And so we do a trick. We actually do 2 of these pulses to give us more time to the echo. But when we talk about proton spectra, when you took organic chemistry, you learned that a typical proton spectrum is from what to what parts per million. What's the typical proton spectra range? Anybody remember? You're not saying?
I'm not even taking.
How many parts per million? 0 to 12. 0 to 10, 0 to 12. Okay. So you're in that range, and there's weird things, and there's cool things too, like a hydride can be like minus 30 parts per million, and a hydrogen bonded thing can be up by 12, 15, whatever. But 0 to 10 parts per million typically corresponds to, on a 400 megahertz NMR, 4,000 hertz in sweep width. This spectrum that I'm looking at here has a total width of at least 250,000 hertz. So it's really, really wide. It's a solids thing. This is like brute force NMR. And the reason we do brute force NMR is I'm not smart enough to know how to do finesse NMR, so we just have these big old power amplifiers, and we just bash the system a little bit. Okay, so let me give you an example of a couple of the spectra that we see. And here's what happens with this polymer where it's on silica, for example. So this is a quadrupole powder pattern. It looks just like a textbook pattern with a methyl group. The red thing here is the simulation. So, you know, if you want to understand what's going on, remember in science you can almost never prove anything, right? all you can do is just have lots of circumstantial evidence that eventually the other party gives up. But what can you prove, really? You can just say, this is consistent with everything that ought to happen, therefore I truly believe that this happens. But you can't prove things. But in this game, you have to do simulations, and you it's like doing reaction mechanisms. You can prove a lot of things that are wrong, but when everything else is wrong and what you have is consistent with everything that you say, okay, I feel pretty confident that this is what's going on. So these are simulations, and some of my group spends time doing simulations. This is the bulk polymer, by the way. And so this is a rigid polymer. This is a polymer that's undergoing its glass transition. And this is just a polymer on something else. So the point is, you can get all these different line shapes. You can fit them. And from the line shapes and their fitting, I can tell you how the molecule's moving and how fast it's moving. That's the point of this slide. So let's take an example. This is my polymer. Turns out it's a moderately low molecular mass polymer. Let me tell you a couple other things. So on the bottom here is what happens when you do differential scanning calorimetry. How many have taken PChem? A couple. Only one. Okay. So, it turns out that you can probably estimate what the heat capacity is of argon, neon, krypton, helium. Turns out, anybody want to guess? Besides Jason? It's 3/2 R. Why is it 3/2 R? Do you remember that? Because all the molecule can do is translate it in the X, Y, and Z direction, and each one of those has 1/2 R in heat capacity. So heat capacities are related to how many ways I can put energy in the molecules. So if I have a frozen polymer, the methyl group rotates. That's a way I can put energy in the molecule. Maybe it kind of wiggles a little bit. Things do move even in glasses, so I can throw energy into there. But when I go through the glass transition temperature, things are wiggling like crazy. You can put lots of energy in there, and the heat capacity changes as you go through the glass transition temperature, from lower to higher. And so you can measure with calorimetry. Calorimetry and measuring heat capacities are all about how much energy do you put in to get a rise in temperature. Okay? So I can measure this with calorimetry, and it turns out that there's a dependence on polymer molecular mass. And these are not error bars. These are the sensitivity of the experiment. This is when I start to see that a glass transition is starting, and this is when I see that it's ending. And I can measure the same thing with NMR. It's a heck of a lot more expensive, but this represents the sensitivity. 20 degrees below where the glass transition temperature starts, I can see that there's stuff going on there. And a glass transition is not like a melting temperature. Remember when you did organic? You guys made something, right? And how did you test its purity in organic? Probably. You did a melting point. And how do you know if it's really pure?
See like an elevation, something like that.
Well, you get a temperature, but what happens? Does it go over a range, or does it go over a very narrow, a broad range or a narrow? Yeah, pure compounds generally melt in a very narrow range. Glass transitions aren't quite like that. They have an inherent breadth. They're more complicated. They're not a first order phase transition. So in any case, 20 degrees below, stuff starts to happen, and then even above, I get to the rubbery material, but they scale differently. These are measurements of the glass transition measured by NMR and by DSC. Here's the NMR measurement. But the point of all this is that there's this weirdness that they're not on top of each other. Why is that? Well, it turns out, I'll use my pen as an example. If I take this pen and I put it in a machine that just twists it, so I hold it on this end and I twist on this end, and I see how much energy does it take to just get a small twist in this plastic pen. And then I do this as a function of temperature, and I see where it goes soft. That's the glass transition temperature. But if I wiggle my pen really slowly versus doing it really fast, I get a different response. And that different response has to do with the fact that Polymers are viscoelastic materials, and their response depends on how much you hit them, or at what frequency you hit them. And you know a material like that. Silly putty. What happens when you stretch out silly putty fast? It breaks. It's a brittle material, right? You get this nice sharp break, and it breaks it. What happens when you pull it out slowly? Right, it stretches. So that material has a viscoelastic response, which is easily demonstrable. I forgot my silly putty. Easily demonstrable based on the rate at which you do something. And NMR measures the rate of about 40 kilohertz, 40,000 hertz. So it's kind of like hitting a baseball kind of rate. But the glass transition temperature measured by DSC measures it at raising the temperature a few degrees a minute. So much slower time scale. And its difference is understood in polymer physics, but basically measures the same thing. But NMR is much more sensitive. So what happens? So that's a lot of stuff, but what's going on? Okay, so here's what I want you to remember. This spectrum up on top here is what I showed you before as a rigid spectrum. This polymer, for practical purposes, the methyl group's whizzing around, but the backbone of the polymer is basically frozen in space. Oh, by the way, I shouldn't do this, but I will. Okay, so cheapest plastic known is probably what? What is the most irritating plastic that you have on a regular basis?
Saran.
Oh, why is that irritating? That stuff is cool.
It just clings.
Because it sticks to everything, yeah. Saran is a copolymer of polyvinylidene chloride and polyvinyl chloride. But which one, what is the plastic thing that breaks that is irritating? Anything like around a hinge that you can think of? About this big?
Door handles.
What?
Door handles. Like
Door
on,
handles.
like a vehicle.
Oh, yeah, no, those are paint. Those are probably filled plexiglass. Yeah, I have an old toilet. My daughter has an old toilet with both door handles. Sunglasses will break, yeah, but there's even something that's even cheaper plastic that breaks more. And you guys may not use them as well. In the old days, there were 78 records, and then they were then they became, those were Bakelite, and then they became vinyl because they were ethylene vinyl acetate copolymers, and now instead of vinyl, you have your iPad. But before the iPad came, the CD. And what is dang annoying about a CD? The cases break, the hinges break, right? You haven't experienced that? You don't have a CD?
Oh, no, I do. I just thought you're talking about scratching the CDs.
Oh, yeah, well, that's probably good.
That's
The
annoying
CDs,
too.
by the way, the CDs are polycarbonate, which is what your safety glasses are made of, your safety glasses that you're wearing. Very impact resistant. And just to show you how brave I am, I'm building an annex to my shed, and I'm going to put a couple of polycarbonate bubbles over there. And we do get a little hail in Oklahoma, but my view is that these polycarbonate bubbles for the what do you call it? The skylights will stand up to Oklahoma hail. That's the principle anyway. The Pope Mobile's made out of polycarbonate. Anyway, so the point of all this is polystyrene is an annoying, brittle plastic, a good example of material that's brittle, but it looks like it's glassy, right? But if you took polycarbonate, hung it from the ceiling, and came back and you measured, sorry, I said polycarbonate, it would also work for polycarbonate, but you took a CD case and you hung it from the ceiling, and you came back and put a weight on it, you came back, tomorrow, and you measured the CD case, same size. You come back 100 years from now, that thing is stretched. Just like, if you're here 100 years from now, that thing is stretched just like a rubber band. So the time scale of these experiments is really critical. Well, I digress. So, hard brittle plastic, softer plastic. Now I'm filling up the middle. Let me jump to here for a second. This is a rubbery material where things are moving like crazy. The motion causes the NMR signal for the deuterium to become narrower. That's generally true of all NMR signals. And in between here, it gradually gets narrower. Somewhere around here is what we call the glass transition temperature, where it's in that intermediate range, and that's the temperatures that we see here. But this is a very uniform process. How the molecule moves is really complicated, but at least it's uniform. All the different parts of my sample behave the same. And so let me look at a series of spectra of different molecular masses, and I want to show you something that's kind of interesting, if this works. I'll just show them all at once because, okay. So basically what I'm just trying to show you is, this is the one that I showed you. This is different molecular masses of these samples. So here's the glass transition temperature, around 50 degrees for the sample. And I showed a molecular mass dependence, but I wanted to show you is that these spectra look kind of the same in this kind of region. The temperatures don't match up perfectly, but the point is, it's around 40 degrees for the 5,000 molecular mass polymer, 25 degrees below, this is the reference. 25 degrees below, 38,000 here, 77K is 0, and 165. And it basically goes like this and asymptotes out. Low molecular mass polymers, the whole molecules move, and that contributes. When you get to high molecular mass polymers, only sections, almost like a crankshaft in a car, move, and that's all that's responsible. The whole molecule doesn't have to move to have a glass transition anymore. So that's the point there. But uniform and monotonic, low to high. That's going to be important in a minute. So I'm going to absorb polymers. Now think of having a ball of string, not wound up, but think about dropping a piece of string on the surface, a long piece of string. Some parts touch the table, some parts are away from the table, some parts are in between, right? So when polymers go on surfaces, you don't stretch them out. They don't generally stretch out and go on really long. And the reason for that, even though enthalpy might want them to do that because they like being attached to the surface. The surface doesn't like air if it's a surface like glass. Glass doesn't like air very much. Put a polymer on there, it sticks. That's why Scotch tape sticks pretty well to glass. So what happens then? Why don't they go flat anymore? Because if it's not enthalpy, it must be entropy. Entropy is all about how you can do things. It's too ordered. Systems like to be disordered generally. And so entropy wants these molecules to go on in kind of a convoluted way. And so you wind up with places where they stick really closely to the polymer, to the silica, places where they're in between, and then you got these dangling ends. And these happen because these materials hydrogen bond to surface silanols. Hydrogen bond is between between oxygen, nitrogen, or fluorine, and hydrogen, right? So this is acidic, this is basic if you want to think of it that way, but in any case, they hydrogen bond, and this makes them stick. So if you, by the way, if you take a solvent and dissolve a polymer in there and stick that in a beaker or something like that, some glassware, you probably have semi-permanently coated beakers. They don't come off very easily. So, okay, so we're going to put these on. The problem is NMR is not very sensitive in some cases. So what we do is we put these on surfaces. And in this case, these surfaces are little balls of silica because they have lots of surface area. And the more specific surface area you have, the easier it is. Because if I take just a piece of glass, I would like to be able to do these experiments on a glass slide. But if I put a really thin coating, I'm talking about 10 nanometers or less on a glass slide, there are just not enough of them in there. So what I have to do is take little balls of silica, and I coat those little balls of silica. It gives me huge surface area. How much surface area? 200 meters squared. In 1 gram of stuff, of this high, small particle silica, you have 200 square meters. So in 1 gram, you've got enough to coat all these walls. It's the same equivalent surface area. Huge surface areas. That's why nano can be so different than macro, because of these surface areas and the size of the particles make things behave differently. So anyway, so we're going to put these, we're going to absorb them from solution. We're going to then let the polymer stick, and then we're going to dry it. So we're looking at materials on the silica air polymer interface. And so here's, oops, oh, there it is. This is the reminder. Remember what I told you before? Uniform. Look, around 45 degrees, you kind of get this triangle pattern, and then it gets narrow and narrow. By 80 degrees, all it is a single narrow peak. Oops. Okay. So now I absorb these polymers. Look at what's going on here. 25 degrees, well, that's the same. 35 degrees, it's not showing much narrowing. 45 degrees, not a lot of narrowing. 50 degrees, remember this is getting 55 degrees, it's getting pretty narrow. You know, the other one was getting pretty narrow, right? So now I'm starting to see a little bit of material where my polymer starts wiggling on the surface. In bulk, it was wiggling pretty good. So my polymer's stuck onto this solid, and it's not moving very much. And then as I heat it up, I get some more material that's moving, starting to move, more material starting to move, and even more material starting to move, but I still have remnants of this powder pattern. So I have the superposition of some material that's moving very rapidly and some material that's frozen. And so on the surface, this material is inherently heterogeneous. I said the polymer, the bulk polymer, was homogeneous. This is heterogeneous on the surface. And that makes sense because remember my picture? You had some segments that looked like they were stuck on the surface and you had other segments that were further away. These are the guys that are further away flapping in the breeze. And these are the ones that are at the interface with the silica that are stuck because of that hydrogen bonding. By the way, if they don't like each other, these bets are off. But these guys like each other. They like the hydrogen bond across that interface. And so here's an example. Here's a bulk polymer. This turns out to be polyvinyl acetate, not polymethyl acrylate. Polyvinyl acetate, by the way, is the polymer that's in a white substance that you all probably messed around with as kids. Anybody want to guess?
Glue.
Elmer's glue, yeah, and other white glues like that. It is also the binder in interior latex paints. And you don't use interior latex paints on the outside because, not because it says it's interior, because the polyvinyl acetate, when it gets hit by light, photo degrades and it'll chalk. And so you use more expensive binders in exterior paints, acrylates and things. But anyway, I'm sorry about the little polymer lesson that we're learning along the way, but I can't help it. So, you know, compared to bulk, we have some material that actually can be more mobile and some material less mobile. So at the air interface, this material is actually more mobile than bulk, and at the silica interface, it's less mobile than bulk. So, let me show you another, hit that about 3 times. Here's the one, hit it one more time. So, remember before what happened when I looked at different molecular masses? I said the TG goes up and then kind of asymptotes. Let's look at this for a second. This is when it's absorbed. And this is just one of the peculiar things. Sometimes when you put stuff on surfaces, weird stuff happens. So, hit one more time. So just to make an example of what's going on here, if you look at one of these right across here, and you can quantify this, but the point is, these guys all look pretty much the same, right? The spectra are identical, and they don't look like any of the other ones this way. They all look like this corresponding one across here. This is one of these things where we were just lucky. It's just that they all corresponded. But let's look at what happens. So this is the one I called 0 degrees before, and if I go lower in temperature, it goes about 10 degrees down it goes about 20 degrees down. And that's kind of what we would expect, but when you go the other way, it actually goes down in temperature as well. If this was a bulk polymer, we would expect this to be at 75 degrees. And I've just moved the spectra up and down so that you can kind of go across with them. So on the surface, the mobility changes, but not in a asymptotic way. It actually goes up and then comes down, which is really kind of weird, but it is. Okay, and in fact, so in bulk, the mobility is higher, but it kind of goes like that. On the surface, it goes down to a minimum and then goes back up. And we can quantify all this, but that's the basic principle. And I should point out, I did it about 3 or 4 times. So you can also see this stuff with calorimetry. Now, I usually give talks to polymer chemists, and they don't understand much of this NMR stuff. They think it's all magic. But they understand calorimetry. And the really weird thing about this is, calorimetry is almost impossible to really understand at a fundamental level because there's just so much going on that you really don't know anything about on a molecular level. And at NMR, you're actually measuring the reorientation of a carbon-deuterium bond. And that's really well understood. You have to learn more. So my point here is that at first glance, calorimetry looks so easy, but it's really complicated to understand. But at a deep level, and NMR is really looks complicated at the first glance, but really is simple in terms of what it can tell you. So to make a long story short, again here, so let's look at a couple different systems. And so let's look at polyvinyl acetate, the one I showed you before. Now this is a derivative of the heat capacity. So the point is, when it's narrow, that's the glass transition temperature for bulk polyvinyl acetate, Elmer's glue, without the water. But when I absorb the polymer on silica, I get a really, really broad material. This is the material close to the surface of the silica, and this is the material that's almost bulk-like. And if you add more than this, and by the way, 1.44 milligrams per meter squared. So I have, on 1 meter squared of surface, I have 1 milligram of polymer. If that was a uniform layer, how thick would that be? Well, if the density is about 1.4 nanometers. That's really thin. It's really a small amount of material. This is really a surface effect. And by the way, when you get up around 1, you see that it starts to look kind of bulk-like. Not exactly bulk-like, but kind of bulk-like. So let's jump up here to the green one, polymethyl methacrylate, plexiglass on glass. Bulk plexiglass looks like this. Adsorbed plexiglass is broader and shifted to higher temperature. Now, what about polystyrene, my cheap brittle plastic? I put that on silica. Remember polymethyl methacrylate and polyvinyl acetate? These guys have carbonyls. They're capable of hydrogen bonding. Does polystyrene have a carbonyl? It's just got a benzene ring, right? It's got, a phenyl ring. It's got a phenyl ring. Not very polar, though, is it? It's a little polar, but it's more polar than polyethylene. But it's not very polar, right? So you wouldn't expect it to stick very well to glass, would you? I wouldn't. So here's the bulk polystyrene, and here's polystyrene adsorbed, and basically not much of a change. Sticks, doesn't stick, sticks. And so you can see the difference between these different materials. Hit the next one. And by the way, this whole business about the thing that I just showed you with NMR is completely the same if you study the bulk and adsorbed polymers. And the adsorbed polymers always have a higher TG. And actually, if you use this line, increases, kind of decreases and decreases more. Just like the NMR one that we showed where the mobility gets lower, and then it goes back up. So, and that's just it plotted. So surface, just kind of asymptotes, and on the, bulk kind of asymptotes on the surface goes back down. Next one. Okay. And again, on silica, on treated silica, by the way, you can take this silica, you can put methyl groups on top of it, right? So we bond, we use hexamethyl trisilazane. You basically put a silicon with 3 methyl groups on it. So you take glass and make it oily on the surface. Polymers that are polar don't stick very much anymore. They stick a little bit and there's bulk. So next slide, if you're doing it. There's a lot of people involved in this. I do very little besides try to motivate people. I'm being charitable to myself. But I have had the pleasure of working with a lot of really talented students, and I've talked about a lot of their work. This is my current research group here. And he's working on superhydrophobic coatings. He's working on new emulsion polymerization techniques. She's working on FTIR block copolymers. She's just starting to looking at absorbed polymers. She's doing diatomaceous earth-based superhydrophobic polymers. She's measuring heat capacities of absorbed polymers. She's doing making some polypeptides that we're trying to absorb, which are a pain to characterize. He's doing contact angle measurements and made a little contact angle. And these are students who have already graduated. And with that, I thank you very much for your attention and apologize for going a little over. I think that's it.